What's the first thing you ever learned about black holes? Do a Google search for black holes and I guarantee that you will find this statement. A black hole is an area of such immense gravity that nothing, not even light, can escape from it. It's the first thing people learn about black holes, and it really is everywhere. It's so common, in fact, that it has become received wisdom, passed from person to person, with everybody repeating it but nobody actually questioning it. Is this the first thing you learned about black holes? If nothing else, is this all you know? If so, you're not alone. But why should anybody question it if indeed a black hole is, according to what has become a mantra, an area of space whose gravity is so strong not even light can escape? They should question it because it just happens to be wrong. Okay, not completely wrong, but exceptionally misleading. And to understand why, let's step back a bit. If you dig a little deeper, it's also often said that light cannot escape from a black hole because at the event horizon the escape velocity reaches the speed of light, and because light cannot travel faster than, well, light, then it cannot escape. This is not correct either. All of this leads many people to see gravity as somehow being so strong it pulls a photon back as if it were attached to a rubber band which is stretched to its full extent before the photon can leave the black hole. Gravity therefore acts like some sort of brake on photons attempting to pass through the event horizon into the space beyond, but this is not what happens. There's another piece of received wisdom which says that light only and always travels in straight lines. Unlike the black hole mantra, our own experience, or experiments we might have done at school, dictates that this one is totally correct and can be relied upon. Until, of course, we start talking about gravitational lensing. Here's an illustration of gravitational lensing from the European Space Agency. In this graphic at top left we have a distant pulsar, a type of rotating neutron star. In the centre we have a galaxy, and bottom right we have the Earth. The galaxy is obviously between the pulsar and the Earth. In this interpretation, light leaves the distant pulsar and is deflected by the mass of the galaxy in the middle of the image. Or to be more exact, the galaxy's huge gravity splits the light into two separate paths, meaning that we see two images of the pulsar from the Earth. Now this phenomenon is well observed and understood and gives us such things as Einstein crosses, which consist of multiple images of distant galaxies as shown in the inset at top right. Here we see some of the foreground lensing galaxy which is bending the light from a more distant galaxy into 5 separate images. But wait a moment, light only travels in straight lines, so how can its path be bent by gravity? And so we finally get to the answers to these questions. The path of light is not being bent or deflected by gravity. It can only travel in straight lines, as we said. It's space itself which is curved by gravity, as stated by Einstein. And because the space the light travels through is curved, the light has no option but to follow that curve. It's like a ball in a roulette wheel. It travels in a straight line, but the space in which it's moving is curved, so the ball has no option but to travel in a circular path. The more the mass, the stronger the gravity and the greater the curvature of space. Now, what do you think would happen in a place where the gravity is so strong, space is curved to extremes? That place, of course, is a black hole, where the physical laws we are familiar with are pushed to their limits. Here you have photons inside a black hole. The space they are travelling through has been warped and bent so much by gravity that the photons can only follow circular paths inside the event horizon. From the photon's point of view, it is moving in a straight line, but the curvature of space is so extreme that it leads the photon on a path which means it can never cross the event horizon. And this is the reason light cannot escape from a black hole. It's not directly to do with gravity or escape velocities, it's more a question of geometry, the geometry of extremely curved space-time, which imprisons photons forever inside a black hole. The extreme bending of space can also be seen in this simulation of a black hole by NASA's Goddard Space Flight Center. It must be stressed that all of this simulation is taken directly from Einstein's equations of general relativity and is not just some random guess. The simulation is, as far as it's possible to tell, an accurate depiction of what happens to light around a black hole as a result of the extreme bending of space-time. Seen edge-on, notice that the black hole's accretion disk appears to flow above and below the event horizon. It doesn't, of course. Space is curved so much in the vicinity of the black hole that light is, again, following a curved path, allowing us to see the part of the accretion disk which is behind the black hole. Watch what happens as the simulation changes to a full-on view and back again, and you will see the effect which curved space-time has on the light travelling through it. Another myth about black holes concerns how they consume matter. Supermassive black holes do not, contrary to what many people seem to believe, swallow their host galaxy. Stellar mass black holes do not wander the universe gobbling up everything in their path. This misconception arises from not understanding how gravity works. Let's investigate. Let me ask you a question. Which has the stronger gravity, a star of 10 solar masses or a black hole of 10 solar masses? Just think about that for a moment. The answer, of course, is neither. Their gravitational fields are of exactly the same strength. Why is this? The only factor governing the strength of a gravitational field is the mass of the object. Objects sharing the same mass will always have the same gravity, and it doesn't matter if one of those objects is a black hole, a star, or anything else. The only thing which matters is the amount of mass. Now let's give our 10 solar mass star a few planets. What do you think will happen to those planets if we replace the star with our 10 solar mass black hole? The answer is, of course, nothing. The planets continue in their orbits unaffected, although pretty soon it's going to get very dark and cold on those planets. But the important thing is that they are still orbiting a 10 solar mass body, so the black hole's gravitational effect on the planets will be no different from the stars. They will continue to orbit the black hole as if nothing had happened. Now let's place the black hole at the centre of a galaxy. Its gravitational influence is strong enough to keep planets circling it, but does not extend further. Remember, this is a 10 solar mass black hole which replaced our 10 solar mass star, so its gravity is no stronger than the star's was. It certainly cannot swallow anything further out in the galaxy. In practice, of course, supermassive black holes at the centres of galaxies can be measured in millions or even billions of solar masses, but the idea is the same. The gravity of the black hole has a finite range which depends solely on its mass. This amazing animation from the European Southern Observatory, compiled from 16 years of infrared observations, shows the movement of stars around the supermassive black hole known as Sagittarius A star at the centre of our galaxy. All of the stars in this animation orbit an unseen, compact object with around 4 million times the mass of our Sun. That mass obviously generates a strong gravitational field, but exactly how strong? So here's a question for you. How many stars in total do you think orbit Sagittarius A star? Bear in mind that there are approximately 1,600 stars per cubic light year at the centre of the galaxy, so how many have actually been pulled into orbit around the black hole? I'll give you a second to think about that. The answer is probably not as many as you might suppose. Only a few thousand stars at the centre of the galaxy orbit Sagittarius A star. even with its mass of 4 million suns, a few thousand out of the estimated 200 billion stars in the Milky Way galaxy. Therefore, contrary to popular belief, Sagittarius A star is not going to swallow the galaxy, still less anything beyond our galaxy. Let's zoom in a bit. The bright star moving rapidly here is designated S2. You can see it looping around the black hole, each complete orbit taking 16 Earth years. At closest approach, it moves at a blistering 17 million kilometers per hour and comes to within 17 light hours of the black hole, or 4 times the Earth-Neptune distance. Yet still, Sagittarius A's gravity is not strong enough to swallow it, even though the star passes very, very close to it, astronomically speaking. In fact, we've never seen any stars being consumed by our local supermassive black hole. The stars orbiting it are simply too far away and moving too fast to be consumed, so please can we put the idea that black holes are consumers of galaxies to bed finally. Occasionally, however, the black hole does swallow lumps of material in the swirling accretion disk of matter surrounding it. This results in a bright flare across many wavelengths, infrared, X-ray, radio. The flash you see in the middle of the screen is one of these flares, which is the result of Sagittarius A star consuming a lump or a knot of material which is orbiting it. This allows us to see exactly where the black hole is, but more importantly, it confirms its existence. This animation conclusively, therefore, demonstrates that there really is a dark, compact, massive object at the centre of our galaxy. Related to this, there's another common misconception that our entire galaxy orbits around Sagittarius A star. Clearly, from what we have seen, it does not. Only a few thousand stars out of 200 billion orbit the black hole. Our galaxy orbits around its centre of gravity, which is, quite obviously, the centre of the galaxy, taking 225 million years to rotate once. So let's kill that myth too while we're at it. And this is it. Sagittarius A star, the supermassive black hole at the heart of our galaxy, as imaged by the Event Horizon Telescope, a global array of radio dishes which form a virtual telescope the size of the Earth. Swirling around it is the accretion disk. The dark area in the middle is not the black hole itself, but an area around it where there are no photons, because any entering that area are immediately pulled in. As Sagittarius A star itself is black because it emits no radiation, as we've seen no photons of any wavelength can escape from inside the event horizon, it's forever invisible, but it's inside that dark area, perhaps occupying 1/10 of its diameter. Well, that brings us to the end of our video about myth-busting black holes. We do hope you've enjoyed it. If you know of any other common black hole myths or misconceptions, we'd be only too happy to address them in a future video. Describe them in the comments, and you can also, of course, ask any questions you may have in the comments too. Do have a look at What is a Black Hole, our video which introduces black holes, and the other videos on the channel, of course. From everybody at Space Odysseys, thank you for watching and goodbye.
So today I'm starting a series on exoplanet discoveries, planets around other stars, other worlds outside our solar system. Of course, the driving motivation for this, besides just general curiosity, is: are we alone? Are we alone in the universe? Maybe the greatest question that is yet to be known or to be solved. Are we alone? So the history of exoplanet detection is fascinating, and with errors and missteps. But today we know of over 5,000 planets around other stars, and it appears that stars with planets are the rule rather than the exception. So the series that we're going to start today is about the different ways we've thought about worlds around other stars, the detection methods we use, the technologies, what those worlds are like, what stars they're orbiting, and of course, do they appear to be habitable? Could they be places where life could develop? So today we're going to start, obviously, with the screen. We're going to start not so much with the science, but with the philosophy, because the human condition, are we alone? The human nature has asked this question for thousands of years. And there have been some notable philosophers who have pondered this. Okay, so again, this isn't science. You're not building observation and theory and testing it multiple ways. This is just kind of thinking about things. So I have some interesting quotes here. Thales of Miletus. Now, Miletus was in Greece, I think, at the time, and then this is, 2,500 years ago, and is now on the coast of Turkey. And he said, "The stars are other worlds. Earth and everything beyond has a common physical basis." This was an incredible statement because up until then, and quite beyond that point, the prevailing thought was that the heavens are pure and pristine because they are the heavens and the residence of the gods, and down here with the unwashed masses on Earth, the physics are different. So this was an incredible statement. Let's see. Anaximander of Miletus, again Miletus, 2,500 years ago or so, he said, "Earth is a cylinder. Sun and stars are fires trapped in globular masses by cooler air." What an interesting thought. I mean, how do you dream this stuff up? Diogenes actually kind of got it right. Well, he got it right and wrong. He thought air was intelligent, and I'm not sure how he came up with that. But he also believed that there were infinite worlds out there in the universe, an infinite number of worlds, and that the meteorites that we see, the meteor showers that we see, came from space. There was a lot of debate over whether they were atmospheric or spaceborne. Aristotle, who we regard as a very wise philosopher, he kind of got it wrong. He said the world contains all the material there is with nothing left over to form any other worlds. So these are just, it's interesting thinking, and unclear how they came about these thoughts. But finally, Isaac Newton, in his great work, The Principia, said that if there are other systems out there, other planets, other stellar systems, they will all be constructed according to a similar design. And that is very similar to the statement of Thales that said that the physics of the universe is the physics of the Earth, and everything is put together in quite the same way. Now, I've saved the best for last because this is my hero. I actually dress up as this guy for Halloween, and his name is Giordano Bruno. And Bruno was a contemporary of Newton and others, and he believed that the sun was a star, just like the stars you see in the night sky, and that the planets orbited the sun. That was still a matter of debate, and that there are many stars and many stellar systems, and that there are planets, and that there could be life on these planets. Now, he was kind of a rogue guy. Okay, he believed in freedom of religion. He believed you should judge people by their deeds and not their works. And so he was actually quite ahead of his time. And so for that, there he is. There's Giordano Bruno. And here on the lower left, he's brought up in front of an inquisition from the church who really didn't like what he was saying, and labeled a heretic. And so he was executed. And here's a famous painting with Bruno on the left in the white garb and the crosses, and the church going to tie him to the stake and burn him alive, which brings to mind the great quote by Max Planck, who said, "Science progresses funeral by funeral." Right? So it takes a lot of courage to, buck the system. We generally believe that 1995 was the first detection of a planet around another star. Actually, to that in just a second. But in fact, there was a detection of a planet around another star in 1917. Who knew? This is an astronomer. His name is Van Manam. And he was looking at high proper motion stars that appear to be moving rather fast across our line of sight, which means they're rather close. and he noticed one that was rather dim that he didn't quite understand. And so he took a spectrum of it. Now, this is back in 1917. They knew very little about stars at that point. In fact, at that point, they didn't even know the galaxy was one of many galaxies. We thought that was all there was. The upper left shows the spectrum of that star, and the two black lines on top and bottom, thick black lines, are references, and the thin line that's broken up in the middle is showing an iron line, iron in the atmosphere of a star. Very unusual. Very unusual. The spectrum in the bottom right is showing a better spectrum of that star that was taken later, showing calcium and magnesium and iron. And what's unusual about that is this star is a white dwarf star, much like our sun, that ended its life and contracted to a dense mass and has some convection going on. And there should be no metals on the surface. These things eventually, over a period of tens or 100,000 years, should make their way as heavy material down to the core of the star. And that means that something's going on replenishing these materials in the surface of the star, which is where we're seeing them. And that means that this star was once the sun of a planetary system, and that you probably have meteorites or other things that are falling into the star, replenishing its heavy elements on the surface. So I will end today. This is just the first in the series with, in fact, the first discovery of a planet around another star. And this was Beta Pictoris, or if you're in a science convection with a lot of nerdy astrophysicists, they'll just say Beta Pic. This is this was a pulsar, a rotating neutron star. It was discovered that the very regular pulses from the star, from the radio emission from the star, would vary a little bit. And they were varying because there's a planet orbiting the star, pulling it away from us, pulling it towards us, and changing its distance. Therefore, we received its signals at different times. So this is the beginning of our understanding that there are, in fact, verifiably, observably, planets around other stars. And in the weeks to come, we're going to be looking at the technologies that have brought us to the point where there are now over 5,000 planets we've observed and detected around other stars, how we've done it, what those planets are like, and could they harbor life. And so I'll just leave it there, hopefully with a tantalizing message, and we'll resume next week.
Thank you again, Lou. I'd like to take us back to Lou.
Oh, thank you. Just a small correction. I got a bit ahead of myself, getting so excited about this series. Beta Pictoris, in fact, is a main sequence star, a little more massive than our sun. And it was the first detection of a debris field around another star. It has belts where the material seems to be cleared away. It has evidence of higher order, what we call metals material. But the first planetary detection was, in fact, around a pulsar, as we just found out about pulsars. And that pulsar had the descriptive name PSR B1257. So remember that name. That's his historic name.
Yeah.
And we'll. This was a sneaky way of getting to do the rest of my series today. But we will continue this later.
The amazing thing about that was that nobody expected planets to be found around a pulsar, because a pulsar is a supernova remnant. And how could the planets have survived the supernova? That's the question.
Yeah. Well, it may be that it could be that they didn't, and in fact, there's some debris field of small asteroids or something like that, material just falling on to the surface. So we've been talking about exoplanets and how exoplanets are thought about. Last time we talked a little bit about the thinking of prominent philosophers. Are there planets around other stars over 2,000 years ago? And of course, we carefully avoided any reference to aliens building the pyramids or Stonehenge, so we avoid that. But we then advanced to the discovery of the first debris field around another star, Beta Pictoris, in 1984, and the first discovery of a planet around any star, which was in 1992 of a planet orbiting a neutron star, in fact, a pulsar. So we are ready. We are now primed and ready for the first detection of a planet orbiting another main sequence star like our sun. So main sequence stars, very quickly, stars are born, they live, they die, and they spend most of their life turning the hydrogen in their cores into helium through fusion. And the stars that do that, which is most stars, those are main sequence stars. So there was a detection of a planet around a main sequence star like our sun, and that star was 51 Pegasi. Let's see if I can bring that up here. There we go. And it's in the constellation of Pegasus, which you see here, the Great Square of Andromeda or the Great Square of Pegasus. You can take your pick, and 51 Pegasi is right there. This was identified in 1995. Queloz and Meyer were looking for exoplanets. And if you think about it, imagine you have a bright halogen headlight on a car that's at night, that's maybe a mile away, okay? It's really far away, but it's at night. So you can see, you can see that halogen headlight. And imagine that you have a grape or a pea right next to it. Enormously hard to see that grape or that pea. So we use indirect methods mostly to find these exoplanets. And the method that they chose to use is called the radial detection method. And this takes advantage of a very well-known concept in physics called the Doppler effect. And you all, whether you heard that phrase or not, you all know what this is. Because if you hear a police car or an ambulance coming towards you, their siren has a rather high pitch, and as it passes you, the pitch lowers. Or if there are any race car enthusiasts, you really hear it. As the race car comes towards you, it's a higher pitch, and as it goes away from you, a lower pitch. So the frequency of the sound changes, and that's true for light too. As an object, an emitter of light is moving towards you, you see a higher frequency of light, and as it moves away, you see a lower. So it looks like, it looks like this. In the upper left, we have some representative star system, yellow star in the center, and a somewhat massive planet orbiting it. And so as the star pulls on the planet, so the planet pulls on the star, and actually moves the star a little bit in a circular motion as they orbit their own center of mass. So that star is at times moving toward us and moving away from us. And you can see that depicted over in the upper right here with those sinusoidal waves. The speed of the star relative to the Earth increases and decreases periodically. And then down on the lower right, we have a cartoon of a spectrum with spectral lines. And you see these spectral lines either shifting left or right, depending upon whether the star is moving away from you or toward you. So that is how they detected that 51 Pegasi b. And here is, in fact, that data. This graph here on the y-axis is the velocity of the star moving away from us or toward us. And then in the bottom, it's a phase angle, but basically it's the phase of the sinusoidal curve. You can think of it as time. And so from this, we can get a lot of information about this planet. Also, if we know something about the star, which we do, because we can look at the star's spectrum, and we can tell what kind of star it is, how hot it is, what size it is. And so by combining these two pieces of information, we know that 51 Pegasi b, and that's, by the way, that's the nomenclature. The first planet that you discover orbiting another star is given the letter B, the second planet C, and so on. So 51 Pegasi B, we know is a large planet, a gas giant. We know it orbits about 0.053 AU from its sun. So it's really, really close to its star, its sun. It has a mass of about half of Jupiter's mass. And because it's so close, as we just found out, talking about orbital dynamics, it only takes a little over 4 days for this planet to orbit. So we have found since then many planets orbiting other stars using this radial detection method. I got this graph here from the NASA Exoplanet Archive, and I'm going to give you the reference for that in just a bit. NASA tracks these things. They track the detections, how many we have today, how many, and what methods were used, and what the physics of these planets and planetary systems are like. And you see on the bottom, the method of detecting these planets is color-coded. And at the very top, you see radial velocity or radial detection method. And in red, you can see about roughly how many planets around other stars we've detected from the radial velocity radial detection method. And as we follow this through in coming weeks, we're going to be talking about each of these other methods of detecting extrasolar planets. So I want to leave you with the NASA Exoplanet Archive. This is just a screenshot I took of it today. And so we know, for example, that there are 5,054 confirmed planets around other stars. TESS, the Transiting Extrasolar Survey Satellite, has confirmed 227 of those. And we have some candidates that we have to work through. But this is the definitive, or I'll say this is certainly a definitive source if you're interested in exoplanets. And I will put that link in the chat.
Thank you.
So that's it for today.
I will put that link in the description of this video for afterwards as well.
Thank you, Andy.
Right, thank you very much for that. Very interesting. I've been following that archive for a long time. It's amazing how it's grown and how quickly it's grown. And there's a lot of really interesting information there. A lot of great graphics and fun facts about exoplanets.
Yeah,
and it's a great resource. So I'd certainly recommend that. Okay.
Welcome to Space Oddities and this edition of An Astronomical Life. Today we're looking at Johannes Kepler, 1571 to 1630. Johannes Kepler played a key role in the profound changes in human thinking during the scientific revolution. In Kepler's lifetime, religion clashed with religion, religion clashed with science, the old ideas of Ptolemy and Aristotle clashed with the new discoveries of Copernicus and Galileo. The superstition of astrology clashed with the science of astronomy. Kepler reflected the times he lived in. Seen through modern eyes, he had somewhat contradictory ideas. He was an unorthodox Protestant, a follower of Copernicus and Galileo. He was a brilliant mathematician and scientist who discovered that the solar system's planets followed elliptical paths, not circular ones. An astrologer whose horoscopes were sought out as among the best available. Such contradictions were not unusual during the scientific revolution. Isaac Newton, who lived in a later time than Kepler, 1643 to 1727, did not work in the way a modern scientist would. Also, a Protestant with unorthodox views, Newton spent more time investigating the true meaning of the Bible's word and on the pseudoscience of alchemy than he did on mathematics or physics. Johannes Kepler's early life and education. Kepler was born on December the 27th, 1571, in the town of Wilderstadt, which lay in the Holy Roman Empire and is now in Germany. His father, Heinrich Kepler, was a mercenary soldier who abandoned the family when Johannes was 5 years old. His mother, Katrina Goldenmann, was a herbalist and healer who later faced accusations of witchcraft. Kepler showed an early aptitude for mathematics and astronomy. Here you can see two events that inspired a young Kepler to study astronomy: the Great Comet of 1577 and a lunar eclipse in 1580. He attended a local school in Leonberg before moving to a seminary school in Heidelberg. Kepler then entered the University of Tübingen in 1589 on a scholarship, initially studying philosophy and theology. He studied under Mythbusting, a prominent astronomer who introduced Kepler to Copernican theory. Academic and professional career. In 1594, Kepler became a mathematics teacher at a Protestant school in Graz, Austria. While teaching, he published his first major work, Mysterium Cosmographicum, the cosmographic mystery, in 1596, which defended the Copernican system and proposed a model of the universe based on geometric principles. In 1600, Kepler moved to Prague to work with the renowned Danish astronomer Tycho Brahe, who had a wealth of precise astronomical data. After Brahe's death in 1601, Kepler inherited his position as imperial mathematician and access to Brahe's extensive data. Major achievements: Kepler's laws of planetary motion. First law, 1609, published in Astronomia Nova, New Astronomy. It states that planets orbit the Sun in ellipses, with the Sun at one focus. Second law, 1609, also in Astronomia Nova. It describes how a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. Kepler's third law, 1619, published in Harmonices Mundi, the harmony of the world. It states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. In 1627, Kepler published the Rudolphine tables, which were more accurate astronomical tables for predicting the positions of stars and planets. This work was based on Tycho Brahe's observations and Kepler's own theories. Optical works. Kepler made significant contributions to the field of optics, including the understanding of the human eye and how lenses worked. In 1604 he published Astronomia Pars Optica, the optical part of astronomy, which laid the foundation for the modern theory of lenses and telescopes. His 1611 work, Dioptrics, detailed the properties of light and how it is refracted through lenses. Kepler designed an improved version of the refracting telescope, now known as the Keplerian telescope, which used two convex lenses and provided a wider field of view. Personal life, marriages and family. Kepler married twice. His first wife, Barbara Müller, died in 1611, leaving him with 2 children. He remarried in 1613 to Susanna Rutinger, with whom he had 6 children, though only 3 survived to adulthood. House of Kepler and Barbara Müller in Gossendorf near Graz. Throughout his life, Kepler faced numerous personal and professional challenges, including financial difficulties, religious conflicts as a Lutheran in a predominantly Catholic environment, and the death of many of his children. Here is an image of Susan Rutinger, Kepler's second wife. Legacy and death. Johannes Kepler died on November 15, 1630, in Regensburg, Germany. He left a lasting legacy in the fields of astronomy, mathematics, and optics. His laws of planetary motion were fundamental to the later work of Isaac Newton and the formulation of the law of universal gravitation. Kepler's contributions to astronomy and science. Kepler's supernova. In 1604, Kepler observed a supernova, now called Kepler's supernova, which challenged the Aristotelian belief in the unchangeability of the heavens. Planetary motion and elliptical orbits. Kepler's discovery that planetary orbits are elliptical rather than circular revolutionized the field of astronomy and provided a more accurate model of the solar system. Keplerian telescope and optics. His design of the Keplerian telescope improved the functionality and power of the telescope, aiding future astronomical observations. Advancements in mathematical astronomy. Kepler's work provided critical advancements in the use of logarithms for simplifying complex calculations in astronomy. Influence on future scientists. Kepler's laws and methods influenced future generations of scientists, including Isaac Newton, who used Kepler's work as a foundation for his own laws of motion and gravitation. Philosophical and theological impact. Harmony of the spheres. Kepler believed in a cosmic harmony and sought to explain the universe in terms of geometric and musical relationships, an idea expressed in his book Harmonices Mundi. Integration of science and faith. Despite facing religious persecution and conflict, Kepler maintained a deep faith and saw his scientific work as a way to understand God's creation. Key publications. Mysterium Cosmographicum, 1596. First major work defending the Copernican system and proposing a geometric model of the universe. Astronomia Nova, 1609. Introduced Kepler's first 2 laws of planetary motion and detailed his astronomical observations and theories. Harmonices Mundi, 1619. Published his 3rd law of planetary motion and explored the harmony of the cosmos. Epitome Astronomia Copernicana, 1618 to 1621. A comprehensive summary of Copernican astronomy, incorporating Kepler's own laws and observations. Impact and recognition. Immediate influence. Kepler's work was not immediately recognized or understood by all his contemporaries, but gradually gained acceptance and acclaim. Long-term legacy. His contributions have had a lasting impact on the fields of astronomy, physics, and mathematics. Kepler is remembered as one of the key figures of the scientific revolution, whose work laid the groundwork for modern astronomy. Commemoration. Numerous scientific terms, concepts and celestial bodies have been named in his honor, including Kepler's laws of planetary motion, the Kepler Space Telescope, and lunar and Martian craters. In summary, Johannes Kepler's life was marked by significant scientific achievements that transformed our understanding of the cosmos. His pioneering work in astronomy, optics, and mathematics has left an enduring legacy that continues to influence science today. Despite personal and professional challenges, Kepler's dedication to uncovering the laws of nature and his innovative thinking solidified his place as a cornerstone of modern science. Remnant of Kepler's supernova, SN 1634. Thank you again for watching this episode of An Astronomical Life. Goodbye.
All right, so get this. Listener sent in some research on dark energy and black holes, and
Yeah.
wow, this is wild.
Yeah.
Yeah, we've got some articles from space.com, the University of Michigan, and Imperial College London.
Okay.
And they all seem to be pointing to this, like, potential link between these two, like, cosmic heavyweight,
Yeah.
black holes and dark energy.
Right.
Like, what if black holes are the source of dark energy?
Yeah, that is mind-bending, isn't it? It really is.
Right. Keeps you up at night.
It really is. We're talking about the very fabric of the universe here.
Yeah.
Think about it.
Yeah.
Dark energy is this mysterious force that's like pushing everything apart, causing the universe to expand at an accelerating rate.
Yeah.
And black holes, well, we used to think of them as these cosmic vacuum cleaners just sucking up everything in their path.
Right.
But this research is suggesting they might be playing a much more creative role.
Okay, so how do we even begin to wrap our heads around this? I mean, black holes and dark energy just seem like they'd be at odds with each other.
Yeah.
One's all about, like, intense gravity, and the other is pushing everything apart.
Right, exactly. And that's what makes this theory so intriguing, right?
Yeah.
It challenges our fundamental understanding of both black holes and dark energy.
Yeah.
One of the key pieces of evidence comes from observations of distant galaxies.
Oh, okay.
Astronomers have been studying supermassive black holes at the centers of these galaxies.
Right.
And what they've found is that these black holes are growing way faster than they should be if they were just swallowing up matter or merging with each other.
So something else is going on, something we haven't been able to explain with our current models.
Right.
And that's where the dark energy comes in.
That's the idea.
Okay.
Researchers are proposing that black holes might be directly linked to the fabric of the universe itself.
Okay.
It's a concept called cosmological coupling.
Cosmological coupling.
As the universe expands, black holes grow, and the amount of dark energy increases. Like they're all dancing together, influencing each other's movements.
Wait, so you're saying that instead of just gobbling up matter,
Yeah.
black holes might actually be absorbing dark energy from the expanding universe.
That's one of the hypotheses.
And as they do that, they contribute even more to the expansion.
Right.
Oh.
And it gets even weirder when you consider what this might mean for the inside of a black hole.
Okay.
We often hear about the singularity at the heart of a black hole.
Right.
This point of infinite density where all the laws of physics break down.
Yeah.
But if black holes contain dark energy, which has this repulsive force,
Right.
it could actually counteract the intense gravity at their core.
So are you suggesting that black holes might not even have singularities?
Yeah.
That this dark energy could somehow smooth things out?
It's a mind-blowing possibility, isn't it?
Yeah.
And it's one that has huge implications for our understanding of how black holes work,
Right.
and potentially even for resolving some of the biggest mysteries in physics.
Okay, I'm hooked.
Yeah.
We need to unpack this further. Where do we start?
Well, let's take a closer look at the evidence from distant galaxies.
Okay,
I think that's a good place to really grasp the scale of this discovery.
let's do it.
Okay, so picture this. You're looking at a galaxy billions of light years away.
Okay.
The light we see from it is ancient, a snapshot from a time when the universe was much younger.
Oh, cool. So like a cosmic time machine.
Exactly.
So what are we seeing when we peer back that far?
What's fascinating is that when astronomers observed these ancient galaxies,
Mhm.
they found something unexpected. The supermassive black holes at their centers were much smaller than they should be. based on our current understanding of how black holes grow.
So, like, these baby black holes weren't keeping up with their growth charts.
Exactly.
Huh.
And then when they compared these ancient black holes to the supermassive ones we see in nearby galaxies, which are much older,
Right.
there was a huge size discrepancy. The nearby black holes were significantly larger than they should have been
Okay.
if they had only grown by absorbing matter or merging with other black holes.
Okay, so something doesn't add up.
Right.
The rate of growth is just way too high.
Yeah.
Is this where the theory of black holes absorbing dark energy really starts to gain traction?
It is. The researchers behind this theory found that the growth of these supermassive black holes correlates remarkably well with the expansion of the universe. It's as if they're growing in sync, fueled by the very force that's pushing everything apart.
Now, how did they actually measure this growth, this correlation?
Right.
We're talking about objects that are billions of light years away.
This is where some incredible technology comes in.
Okay.
The Dark Energy Spectroscopic Instrument, or DSI for short.
DSI.
It's essentially creating a 3D map of the universe,
Oh.
allowing us to measure the expansion with incredible precision.
So DSI is like the ultimate cosmic cartographer then.
Right.
It's mapping out not just where things are, but how they're moving and changing over time.
Precisely. And the data from DSI seems to support the idea that the density of dark energy is increasing, which, according to this theory, would be directly related to the growth of black holes.
Okay, so we have these observations of distant galaxies.
Right.
The unexpected growth of supermassive black holes.
Yeah.
And then we have data from DSI that is suggesting an increase in dark energy density.
Right.
It's all starting to come together, isn't it?
Yeah.
But I still keep coming back to this idea of the singularity.
Okay.
If black holes contain dark energy,
Yeah.
does that really mean there's no point of infinite density at their core?
That's the big question.
Yeah.
And one that physicists are still grappling with.
Okay.
The traditional view of a singularity.
Right.
Is that it's a point where gravity becomes so strong that it crushes everything down to an infinitely small point.
Right. A point where our current laws of physics just break down.
Exactly. But if black holes are indeed absorbing dark energy and growing in sync with the universe,
Right.
it suggests that the singularity might not be as singular as we once thought.
So instead of this point of ultimate collapse, there might be something else.
Right.
Something, well, less singular.
It's possible. Perhaps the dark energy within a black hole creates a sort of counter pressure,
Okay.
a force that prevents the complete collapse into a singularity.
So maybe it's not a point of infinite density,
Yeah.
but rather a point of intense density
Right.
balanced by this repulsive force of dark energy.
That's a very intriguing way to think about it.
Yeah.
And it's one of the reasons why this theory is causing such a stir in the world of cosmology. It has the potential to reshape our understanding of black holes,
Yeah.
dark energy, and perhaps even the very nature of gravity itself.
This is wild. We've come a long way from black holes just being cosmic vacuum cleaners, haven't we?
We have, and there's still so much more to explore.
Right.
For example, if black holes are indeed fueled by dark energy,
Yeah.
what are the implications for the ultimate fate of the universe?
Ooh, good question. Does this mean the universe will just keep expanding forever?
Yeah.
Or could something else happen?
Well, let's dive into those possibilities.
So, okay, we've established that black holes might be fueled by dark energy.
Right.
And that has like some pretty major implications for how we understand the universe.
Yeah.
But where do we go from there? What happens in the long run?
Well, that's a question that has cosmologists scratching their heads.
Okay.
There are a few different scenarios, all depending on like the nature of dark energy
Right.
and how it continues to interact with black holes.
All right. Lay it on me. What are the options?
One possibility is that the universe keeps expanding faster and faster, leading to what's called the Big Rip.
The Big Rip.
Yeah.
Doesn't sound too pleasant.
No.
What would that look like?
Essentially, the expansion becomes so powerful that it overcomes all other forces,
Oh, wow.
even the forces holding atoms together.
Mm.
Galaxies would be torn apart, stars would be shredded,
Wow.
and eventually, even matter itself would be ripped apart.
So not just things moving away from each other, but everything disintegrating on like a fundamental level.
Right.
That's a pretty dramatic ending.
It is a dramatic scenario, yes, but it's important to remember that it's just one possibility.
Okay.
Another scenario is the Big Crunch, where the expansion eventually slows down and reverses.
So instead of ripping apart, everything collapses back in on itself.
Exactly.
Like a cosmic rewind.
Yeah, it would be like the universe playing a giant game of cosmic expansion and contraction.
Right.
And then, of course, there's the possibility that the expansion continues at a more or less steady rate,
Okay.
eventually leading to a heat death.
Okay, so we've got the big rip, the big crunch,
Right.
and the heat death.
Yeah.
That's a pretty wide range of outcomes.
It is.
It seems like the fate of the universe really hinges on like what this dark energy is all about and how it interacts with black holes.
Absolutely. And it's not just about the grand fate of the universe either.
Right.
This research has implications for so many other areas of astrophysics.
Okay.
You know, understanding the connection between black holes and dark energy could help us figure out how galaxies form and evolve, how matter is distributed throughout the universe, and even shed light on some of the most fundamental laws of physics.
It's amazing to think that something as seemingly destructive as a black hole could actually be playing such a vital role in the universe.
Yeah.
I mean, we've gone from thinking of them as cosmic vacuum cleaners to potentially the engines of cosmic creation.
Yeah.
It really shifts your perspective, doesn't it?
It does. It highlights the fact that we're still just scratching the surface when it comes to understanding the universe.
Right.
Every new discovery opens up more questions, more possibilities, more mysteries to explore.
And that's what makes it so exciting, right?
Yeah.
This constant sense of discovery and wonder.
Right.
We're lucky to be living in a time where these kinds of breakthroughs are happening.
Absolutely. Who knows what other mind-boggling discoveries await us as we continue to peer deeper into the cosmos.
Well, I, for one, can't wait to find out. So for everyone listening, keep those minds curious, keep asking questions, and keep looking up at the stars. You never know what secrets they might reveal next.
Hello, and welcome to another in the Space Oddities series, An Astronomical Life. In this episode, we'll look at the life and work of Subrahmanyan Chandrasekhar, an Indian-American astrophysicist who won the 1983 Nobel Prize for Physics. He made significant contributions to the understanding of stellar evolution, including the Chandrasekhar limit for white dwarf stars. His work laid the foundation for modern astrophysics. Chandrasekhar's journey from a young boy in India to a Nobel Prize-winning scientist is a story of passion, perseverance, and brilliance. Chandrasekhar was born in Lahore in India, now in Pakistan, in 1910. During his early education, he showed an exceptional aptitude for mathematics and science. He pursued his undergraduate studies at the University of Madras, where he graduated with a degree in physics in 1930. His academic excellence earned him a scholarship to the University of Cambridge in England, where he completed his PhD under the guidance of the renowned physicist R.H. Fowler. One of Chandrasekhar's most significant contributions to astrophysics came very early in his career. While still a student at Cambridge, he developed a theory relating to the evolution of white dwarf stars. White dwarfs are the ultra-dense remnants of stars like our Sun, to which they shrink and cool after they have passed through their red giant stage. About the size of the Earth, they are so dense that their mass is comparable to that of the Sun, so a teaspoonful of white dwarf material would weigh about as much as an elephant. If a white dwarf orbits a parent star, its immense gravity can pull hydrogen off the parent star so that it accumulates on the surface of the white dwarf, adding to its mass. But this process cannot continue indefinitely. Chandrasekhar discovered that there is a maximum mass, now known as the Chandrasekhar limit, beyond which a white dwarf cannot remain stable. This limit is 1.44 times the mass of the Sun. Once the white dwarf exceeds this limit, a huge thermonuclear explosion occurs on the surface of the white dwarf, blowing its outer layers into space. With the white dwarf's mass now below the Chandrasekhar limit again, the process repeats. This chain of events is known to astronomers as a nova. However, if the temperature at the core of the white dwarf is sufficiently high, nuclear fusion occurs, suddenly blowing the white dwarf completely apart in an explosion known as a Type 1a supernova. Chandrasekhar's discovery of the eponymous limit and other groundbreaking work laid the foundation for our understanding of the life cycles of stars and earned him widespread recognition in the scientific community. Despite his early success, Chandrasekhar faced significant challenges. His ideas were initially met with skepticism, and he had to defend his work against some of the most prominent scientists of his time, including Sir Arthur Eddington and Edward Arthur Milne. However, his determination and unwavering belief in his theories eventually won over his critics, and his work became a cornerstone of modern astrophysics. In 1937, Chandrasekhar moved to the United States, where he joined the faculty at the University of Chicago. He spent the rest of his career there, making numerous contributions to various fields of astrophysics. His research covered a wide range of topics, including the structure and evolution of stars, black holes, and the dynamics of stellar systems. Chandrasekhar's work was characterized by its depth and rigor. He was known for his meticulous approach to research and his ability to tackle complex problems with elegance and precision. His contributions to the field were not limited to theoretical work. He also made significant advancements in observational astronomy and played a key role in the development of modern astronomical techniques. In recognition of his outstanding contributions to science, Chandrasekhar was awarded the Nobel Prize in Physics in 1983, along with William A. Fowler, for their work on the structure and evolution of stars. This prestigious honour was a testament to his lifelong dedication to advancing our understanding of the universe. Beyond his scientific achievements, Chandrasekhar was also a passionate advocate for education and mentorship. He was deeply committed to nurturing the next generation of scientists and played a pivotal role in shaping the careers of many young researchers. His legacy lives on through the countless students and colleagues he inspired throughout his career. Chandrasekhar's impact extended beyond the realm of science. He had a keen interest in literature and music and was known for his love of poetry and classical music. His multifaceted personality and intellectual curiosity made him a beloved figure in both the scientific and cultural communities. Subramanian Chandrasekhar passed away on August 21st, 1995 in Chicago, Illinois. His contributions to astrophysics continue to shape our understanding of the cosmos, and his legacy as a brilliant scientist and mentor remains an enduring source of inspiration. Well, we hope you've enjoyed this episode of An Astronomical Life. Do be sure to check out other episodes in the series. You'll find them on the Space Oddities channel in the An Astronomical Life playlist. Also, don't forget our Tuesday live streams at 8 PM UK time every Tuesday, where the Space Oddities team, an international group of astronomy communicators, bring you the very latest astronomy and space exploration news, discussion, presentations, and a lot more. If it's happening in space, it's happening on Space Oddities. Subscribe to the channel and click the notification bell so you always get to know when we upload new content. Thank you so much for watching, and goodbye.